Hey, so this is Joseph, and this is the second part of the second chapter of Stewart's calculus. And I'm going to be talking about the points on a function at which we can't take the derivative of that function. And there are four big points at which this happens. They're non-differentiable points. Alright, so these are the four times when on a curve, if you have any of these four things, you can't take the derivative at that point or points. So first, we've got a Cus point. I'm going to tell you what that means later. 2, we have any point of discontinuity. 3, you've got a vertical tangent. If that's the tangent to that graph, if it's vertical, then that means that the function's undefined there and you can't take the derivative. And 4 is an endpoint of a function. And I'm going to go over all of these right now. So first, we're going to start talking about Cus points. And so Cus points broadly are anytime you have a really harsh point in a function. You can look at it like that. So if you've got a function that looks something like this, that point right there, that's a Cus point, because you have the same concavity of the function on either side. However, the increasing, decreasing, they're different. Or you can have a Cus point can also look something like this. You got a function like that. And right here where the concavity is different. But the yeah, so that's a Cus point too, and it's anytime you have a point. And I'm going to prove to you here, because functions like this, it looks like you could probably take the first derivative, but I'm going to prove to you one thing, and then the second thing you're going to have to take my word for it. First, I'm going to prove to you that you can't take the derivative of a Cus point. Second, I'm going to show you that the tangent to that point, in some cases, is vertical. So here we've got one of the most common functions with a Cus point, and that is y equals the absolute value of x. And now I'll write that out in standard notation. Got these little bars, if you remember, x. And this can also, as we're going to try to take the derivative of this function when x equals 0, I'm going to write this out in a form that's easier to take the derivative of. And that's as the piecewise y equals x when x is greater than 0, and y is equal to negative x when x is less than 0. Okay, so this is our function, and we're going to try to take the derivative when x equals 0. And I'm going to do it based on the definition of the derivative, as we were talking about in the previous video. So we're trying to find y dx of 0, and that should equal the limit as x approaches a, the absolute value of x minus the absolute value of a over x minus a. And so we can solve this because we think of it as a piecewise function. And so this will equal, in these big curly braces, the limit as, and since we're trying to find it at 0, remember a is 0, the limit as a approaches 0 from the positive side of x minus, or sorry, because from the positive side we just get x, so we get x minus 0 over over x minus a, and so that's over x minus 0 as well, and we get that side equals 1. And now we'll try to take it from the negative side of 0, so we get the limit as x approaches 0 from the negative side. And remember, the absolute value function when x is less than 0 is negative x. So we'll have negative x plus 0 over x minus 0, and that gives us negative 1. And so we're taking the same limit, and the same derivative basically. We're taking the same derivative of the same function as x equals 0, and when we approach it from two different sides, we get two different answers. That means that the derivative does not exist at x equals 0 at this Cus point. So you can't take the derivative of a function where it has a Cus point. And it's not completely differentiable if that function has a Cus point. Alright, so now we've talked about two different places where, or one place where we can't take the derivative of a function. Now the second, point of discontinuity. And this kind of makes sense that we aren't able to take derivatives here, because if you have say a jump discontinuity or an infinite discontinuity, the function does, with the jump, the function does exist at that point where the discontinuity happens, but that limit doesn't exist, and because the derivative is a limit at that point, the derivative won't exist there either. You need 2 points on either side of a point. You need at least 2 points on either side of the point at which you're trying to take the derivative, because remember, we're trying to get the slope of the line that passes through that one point, and we need points on the other side to do that. And for an infinite discontinuity, we don't even have a value of the function at that point, so you definitely can't take the derivative there. And so that kind of makes sense. But it gives us this nice little corollary here, which states that if f is continuous at a, then it is differentiable at a. So you know that means if you have a function that's continuous, like a polynomial, for example, then it is differentiable for all points a. And this continuity, the exception to it, of course, are Cus points, and there's an exception at the Cus point because of that vertical tangent that goes through that point, which you just have to take my word for, and the fact that the derivative simply doesn't exist, the limit doesn't exist there. And now, thirdly, we can move on to vertical tangents. That kind of makes sense that it's not going to be differentiable there because it'll be undefined. And the times that we have vertical tangents on a graph that isn't at a Cus point are things like a sideways cubic graph or a cube root graph that looks kind of like this, broadly, except right there it gets a little flatter and you'll have a vertical tangent at that point of inflection. And then you got endpoints of a function. Say you're only dealing with a parabola that exists between x equals 2 and x equals 0. Even if those endpoints are inclusive, you can't take the derivative there at those endpoints because you need a point on the other side of the point that you're taking the derivative of. Because remember, if you imagine making a line go through that point and through other points that are getting consecutively closer, if you don't have a point on the other side, you can't draw that line. So you can't take the derivative at those endpoints.